Dear students, welcome to the first session of Chapter 3 Classification of Elements and the Periodicity in their Properties. Today, we will continue with our periodic trends. And the next trend is ionization energy or ionization enthalpy. So both the words are same itself. Ionization energy can be represented by IE, whereas ionization enthalpy we have to represent with delta HI, change in enthalpy. Now, what is ionization? It is the removing of an electron from an atom or ion. So, from an atom or ion, if we lose one electron or we want to remove one electron, we say the word ionization. And for that, how much energy is required? It is termed as ionization energy. So, how we can define? The energy required to remove an electron from an isolated gaseous atom or ion is called ionization energy or ionization enthalpy. So how much energy is required? It is termed as ionization enthalpy, and it is expressed in the units of kilojoules per mole. If the atom is neutral, then how we can define the ionization energy? It is said to be first ionization enthalpy. If the atom is neutral, how we define the ionization energy? As first ionization enthalpy. And the example is here, X is a neutral atom plus the energy required to remove an electron is said to be the ionization or the first ionization enthalpy. When you remove or lose one electron from the neutral atom, what happens? It becomes X plus one electron. So this energy is termed as first ionization enthalpy. The energy required to remove an electron from an isolated monovalent cation. If instead of this neutral atom, if it is a monovalent cation, it is termed as second ionization energy. See, one example is given, X plus. This is a cation, or one only plus charge is there. That's why it is termed as monovalent cation. From this, if one more electron is to be lost, we get what? X plus 2 plus charge will be there, plus one electron is there. This energy, what we needed or how much we require for removing an electron from a cation is termed as second ionization energy. So this way we can define the first ionization enthalpy and the second ionization enthalpy. The second ionization enthalpy will be higher than the first ionization enthalpy. And this statement, how we are proving is, it's more difficult to remove an electron from a positively charged ion than from a neutral atom. It's very difficult to remove the electron from a cation, and it is also given the reason as what? The cation has greater effective nuclear charge than the neutral atom, and that's why it's very difficult to remove the electron from a cation. In the same way, the third ionization enthalpy will be higher than those of the second, and so on. So it will go like that. So whenever the number of ion or the ionic state is more, the ionization enthalpy will be higher compared to the others. Now let's see the factors that affect the ionization enthalpy. The size of the atom, that is, ionization energy decreases as the size of the atom increase. The nuclear charge. Ionization energy increases with the increase in the nuclear charge. The type of the electron. It depends upon the shielding effect and penetration effect, and also the electronic configuration. As we know that noble gas is having a complete valence or the stable octet configuration they are having, so they possess what? Very high ionization energy. Now let's see the periodic trend along the group and also along the parent. When you move down a group, what happens? We know that nuclear charge increases, effective nuclear charge is almost constant going down the group. then the number of shells increases, and that's why the size or the atomic size also increases. And there's an increase in the number of inner electrons which shield the valence electron from the nucleus. With these all points, we can understand that ionization energy decreases down the group. So due to these reasons, it decreases down the group. Now along the period when it comes nuclear charge, what happens? It increases, or effective nuclear charge increases, and also the atomic size decreases along the period. With these 2 points we can explain that, or we can clarify that ionization energy increases along a period. But still there are some exceptions, and that is what the ionization energy of beryllium is higher than that of boron, and also ionization energy of nitrogen is higher than that of oxygen. That we will discuss how it happens. A graph is plotted against the group number and ionization energy, and the group numbers from group 1 to 18 is mentioned in the x-axis, while ionization energy in the y-axis in kilojoules per mole is measured. Now you can see here the groups. It is the first group: hydrogen, lithium, sodium, potassium coming. Second group: beryllium, magnesium, calcium, boron, aluminum, gallium, carbon, silicon, germanium, nitrogen, phosphorus, arsenic, oxygen, sulfur, selenium, fluorine, chlorine, bromine, neon, helium, neon, argon, krypton. These all are in the groups. Or we can say here along the period also the electron or the elements are mentioned. Now when the plot is drawn, how it is along the period it increases, and along the group it decreases. That is, ionization decreases along the group and ionization energy increases along the period. Now let's see this question, that how or why the ionization energy of beryllium is higher than that of the boron. Why it is higher? In beryllium, we know the electronic configuration according to Offer principle is 1s2, 2s2. 4 electrons are there, and that is arranged in these 1s and 2s orbitals. The electron removed during the ionization is an s electron. The last or the outermost electron is 2s, and from there the 1 electron will be lost. But if you take the boron, we know that boron is having atomic number 5. So the configuration we have to write it as 1s2, 2s2, 2p, 2p1. So the electron should be removed is 2p. That is, p electron should be removed. Okay, so 2p1 it is written, this 1 electron should be removed from the boron in case ionization is there. The penetration of a 2s electron to the nucleus is more than that of a 2p electron. Hence, the 2p electron of boron is more shielded from the nucleus by the inner core of electrons than the 2s electron of beryllium. That's why it is easy to remove the 2p electron from boron compared to the removal of 2s electron from beryllium. Therefore, the boron will be having the small or smaller first ionization enthalpy. That's why we have to say that beryllium is having higher ionization enthalpy compared to boron. The same way we can explain the nitrogen's ionization energy is higher than that of oxygen. The electronic configuration, if we write, how we can write? The atomic number of nitrogen is 7. So how we can write it as 1s2, 2s2, 2p3. So the electron, if it is to be lost from where? From this 2p orbital, that is, p is having 3 electrons. The 3 2p electrons reside in its different atomic orbitals according to the Hund's rule, that is 2px, 2py, 2pz the electron will be. Whereas in the oxygen atom, where the atomic number is 8, 1s2, 2s2, 2p4, we will write the electronic configuration. So the 4 electrons should be in the 2p orbital. And how they will be occupying? In the first orbital, 2px, it will be having 2 electrons in opposite spin. 2py and 2pz will be having single electrons. And the electron which is removed from this is, or it is very easy to remove what, 2p4 electron. Why? Because there the 2p orbital is resulting in an increased electron-electron repulsion, and consequently it is easy to remove the fourth electron, which is in the 2p of oxygen, and it is easy to remove. The next periodic trend is electron gain enthalpy, or delta Heg. Now, how we can explain the electron gain enthalpy? When you take a neutral gaseous atom and you add an electron, it is converted into a negative ion, that is anion. And during this process, what enthalpy change or the energy change is accompanying is termed as electron gain enthalpy, or the other name of that one is electron affinity. And in the form of equation, when we represent, it can be written as x plus electron giving x minus plus energy. This energy which is released is termed as electron gain enthalpy. Depending upon the element, the process of adding an electron to the atom, it can be either exothermic or endothermic. Now, what we can explain about the endothermic and exothermic reaction? During some of the reaction, the heat energy is liberated and it is said to be exothermic reaction. When the heat energy is absorbed or it is taken in, it is said to be endothermic reaction. For many of the elements, the energy released when an electron is added to the atom, the electron gain enthalpy is negative. Remember this point, the electron gain enthalpy will be negative. Now let's see the factors which affect the electron gain enthalpy. The first one is ENC. With the increase in effective nuclear charge, the force of attraction exerted by the nucleus on the electrons increases. So what happens is the atom has a greater tendency to attract additional electron. That means the effect electron gain enthalpy increases and it becomes negative, more negative. The second factor is the atomic size. With, with in decrease in size, effective nuclear charge increases. But what happens? Electron gain enthalpy increases. The next point is the electronic configuration. The value of electron gain enthalpy depends upon electronic configuration of elements and the elements with suitable electronic configuration with lower value of EGE, that is electron gain enthalpy. And the example is like noble gases have practically zero or positive electron gain enthalpies. And this is why, or because they have no tendency to gain an additional electron as they have already filled or they have stable configuration, that is Ns2Np6. The same way we can explain one more, that is halogens have high electron affinity, and this is due to their strong tendency to gain one more electron to become stable configuration, that is Ns2Np6. So they have more electron affinity and it is due to the to become stable configuration. Now let's see the periodic trend of electron gain enthalpy along the period and as well as in the group. Electron gain enthalpy increases in a period and it becomes more negative, and it is because the atomic size decreases along the period, and therefore what happens, the force of attraction exerted by the nucleus on the electron will increase. Consequently, the atom has a greater tendency to attract the electrons, and that is we are saying its electron affinity increases along the period. If we take in a group, what happens? The electron gain enthalpy decreases because the atomic size increases there, and the effective nuclear charge decreases, and thus the electron affinity also decrease. So this is the trend along the period and also the in a group. Now we can explain two questions. That is, electron gain enthalpy of oxygen is less than that of the sulfur. Same way, the electron gain enthalpy of fluorine is less than that of the chlorine. Now both these questions, the same answer we can give. These two elements, oxygen and sulfur, belongs to the same group. Fluorine and chlorine belongs to the same group. And why the electron gain enthalpy of the first element of that or the second element of that group is less compared to the third element of the group. And the reason how we can explain is the electron gain enthalpy of either the oxygen or fluorine is less than that of the succeeding element we said. This is because when an electron is added to oxygen or fluorine, the added electron goes to the smaller n is equal to quantum level, or we know that it suffers significant repulsion from the other electrons present in this level. For the n is equal to 3, what happens? The quantum level S or chlorine, the added electron occupies a larger region of space, and the electron repulsion is much less, and that's why this electron gain enthalpy of oxygen is less compared to the sulfur or chlorine in the same group. The next periodic trend is electronegativity. How we can define electronegativity? It is the tendency of an element in a molecule to attract the shared pair of electron towards itself is known as electronegativity. So in a molecule, the element will be having a tendency to attract a shared pair of electrons, and this is termed as electronegativity. As we know that the gain of electron is also here. Gain of electron is there. Only the thing is the word coming, it is to attract the shared pair of electron. So electronegativity and electron affinity both are almost same only. And if we see the periodic trend along the period or along the group, how it varies we will see. In a group, the effective nuclear charge remains constant, but the nuclear charge will increase in a group. Same way, the number of shells increases when you go down the group. Atomic radius, that's why, increases. The force of attraction between the added electron and the nucleus, then what happens? It decreases. And therefore, we can say the electronegativity decreases down the group. So, these are the reason why the electronegativity is decreasing down the group. If we take along the period, what happens is the nuclear charge and also the effective nuclear charge both increases. The number of shell remains the constant. It's the same along the period. Atomic radius, what happens? It decreases along the period. And the force of attraction between shared electron and the nucleus increases. Therefore, we can say that electronegativity increases along a period. So this way we can explain the periodic trend of electronegativity. And through a graph, we can understand this thing also. That is, when you plot a graph along the x-axis atomic number and also y-axis electronegativity. If we have taken here the groups, you can see here lithium. So not groups, sorry, the period. Period we have taken lithium to fluorine. The second period is taken. Third period sodium to chlorine. Like that, if we have taken, we can see that as the atomic number is increased, what happens? The electronegativity increases along the period. If we take along the group, what happens? It is having a decrease. So this way we can understand that what about the periodic trend of electronegativity along the period and along the group. This is a summary of our periodic trend of the elements in the periodic table. So with this we can understand that how is the trend along the groups and along the parents. Thank you. We'll continue in the next session.